Hey everyone, I'm Arjun Kodinor, the CEO and co-founder of Tutors for Change. Today, we're announcing the launch of our new and exciting educational video development program, where people can submit videos of themselves teaching basic, advanced, or cool and interesting topics in any educational field of their choice. It's wide open. If you're interested in joining this initiative, fill out this Google form. You can also find the link in the description below. Here's a demo video of Sebastian Rossi, one of our tutors and members of our exciting ideas and research team, teaching a topic on the geometry behind the quadratic formula. Hope you enjoy.
Hello everyone, my name is Sebastian and I'm a tutor with Tutors for Change. Today we're going to be going over sort of a geometric derivation of the quadratic formula. If you're watching this video, I assume that you are at least somewhat familiar with the quadratic formula and have probably seen it before in your math classes. Just as a reminder, when we're thinking about the quadratic formula, what we want is we're looking for the roots of a quadratic equation, which I've written here as ax squared plus bx plus c, where a, b, and c are just constants that are given to us. And what we're trying to do is to find the roots of this equation. We want to find the values of x for which this equation is equal to 0. Now, before we get started, what I'm going to do is I'm just going to simplify everything a little bit by, first of all, subtracting the c, the constant term, from both sides, and then dividing everything by a. So what that's going to leave us with, it's going to leave us with x squared plus b over a x equals minus c over a once again. And what I've done down here is I've drawn 3 different rectangles, and the areas of each of these rectangles corresponds to the value of one of the terms in this equation. So first of all, looking at the red square, which has side lengths of x, what we'll see is that the area of the square is equal to the value of this term in our equation x squared, because if you have a square with side lengths of x, then the area is just the product of the two sides, which is equal to x squared. Similarly, for the green rectangle, it's not a square this time, because we have one side length of x and one side length of b over a, but we can still find the area by taking the product of the two sides, and that's equal to b over a times x, which is the second term here. And then finally, the sum of the areas of these two rectangles is equal to the area of this blue rectangle, which here on the right hand side is just minus c over a. Now, in the case of the blue rectangle, we're not really worried about the side lengths as much as the area, because really what we're doing in this equation geometrically is we're equating the areas of these different shapes. So moving on, first thing I'm going to do is I'm going to split this green rectangle down the middle, and I'm allowed to do that because that's not really changing the area. But what we're left with is once again, we're left with an x squared because the rectangle, or the red rectangle, doesn't really change. Plus, and now we have 2 green rectangles, but instead of having side length of b over a, they have side lengths of b over 2a, because we're dividing this bottom side in 2. So the areas is going to be equal to 2 times b over 2a times x, and the x side doesn't really change. And since we're not changing anything on the left-hand side, the area of the blue remains the same. Now, what I'm going to do is I'm going to combine the red and the green rectangles by taking one part, or one half of the green rectangle, and putting it on the top of the red square, and the other one I'm going to put it on the side. And algebraically this doesn't change anything, but geometrically what we can see is that it sort of gives us an idea of how to simplify this a bit, because really what we have is a square, almost a square. The only thing that's missing is sort of this little corner. And what we're going to do is we're going to fill in that corner by adding a yellow square with side lengths of b over 2a to both sides. And again, because now we are adding area to the left hand side, we have to add the same amount to the right hand side. So the reason that the side lengths are b over 2a, just to recap, is because here we have this side of the green rectangle has area of x, and then the second side has area of b over 2a. So therefore the area of the square, if we want it to line up well with these green rectangles, or the side lengths, I mean, of the yellow square, if we want it to line up with these green rectangles, is going to be b over 2a, so that it fits well. And algebraically, what this looks like is we're going to have x squared plus 2 b over 2a x. Just write that a little better. And then now we're adding this b over 2a. And in this equation, we're thinking about the areas of all the shapes. So the area of the yellow rectangle is going to be the side length squared, or the yellow square. It's going to be the side length squared. And then on the right hand side, we have minus c over a. And we're going to be adding this b over 2a squared term to both sides just to keep everything equal. Okay. And now what this allows us to do is now all of a sudden on this left hand side we just have a single square, and the side lengths are equal to sort of this side of the green rectangle, this b over 2a side, plus the x, which is the side length of the red square. So what we can do is we can simplify the expression for the area of the sort of combination of rectangles into a single term that looks like x plus b over 2a, since that's the length of each side, squared, so we get the area, and that once again is equal to minus c over a plus b over 2a squared. And what I'm going to do is I'm just going to algebraically simplify the right hand side of this equation, and what that looks like is we're just going to have x plus b over 2a squared equals minus c over a. Now we are sort of distributing the square, so we're going to have a b squared over 4a squared since we distributed to both the numerator and the denominator. And sort of the last step we can do is we can sort of get a common denominator here by multiplying everything by 4a, and then that way we can combine the numerators into b squared minus 4ac over 4a squared. So next step after that, since we have sort of one fraction here, is we can take the square root of both sides. And we have to remember when we take the square root, we have to remember to keep both the positive and the negative roots. So that means this is equal to plus or minus the square root of b squared minus 4ac all over, skip this step, 4a squared. And what that allows us to do is, first of all, now we can subtract the b over 2a from both sides to get the x by itself on the left hand side. And also, you'll notice that we have a 4a squared in the denominator inside the square root, and we could take the square root of that. So then what that leaves us with is we're going to have a negative b over 2a plus or minus square root of b squared minus 4ac, and that'll just be in the denominator, all over 2a, now that we've simplified square root of 4a squared. And since these denominators are the same, we can combine the numerators into a single fraction, and we're left with negative b plus or minus the square root of b squared minus 4ac all over 2a, which is the form you're likely used to. Okay, so just a recap of what we did. We started out with the formula for a quadratic equation, and we just set it equal to 0, as you do when you are trying to find the roots of it, and simplified it a little bit. The key step here is really sort of filling in this missing piece of the square, because you might be familiar with this technique, or this technique is known as sort of completing the square. And when you look at it in sort of a geometric picture like this, the reason that it's called completing the square becomes quite obvious, because all we're doing is we're completing this larger square by filling in sort of this missing piece. And that missing piece has side lengths of b over 2a. And from there, we can simplify the expression for the area of these 4 rectangles into the expression for the area of a single square with a new side length. And after that, it's just a little bit of manipulation to get the right hand side into a nice form to take the square root of it of both sides, and that gives us the final result. Thank you.